Welcome to our exploration of angular kinematics in human movement. In this video, we'll dive into the fundamental concepts that describe how our bodies rotate and move through space. We'll cover the relationships among key angular kinematic variables such as displacement, velocity, and acceleration, and see how these relate to linear motion. Whether you're a student of biomechanics or simply curious about how the body works, this journey will help you understand the science behind every twist, turn, and rotation. Let's begin by setting the stage for why angular kinematics is essential in understanding human motion. Before we get into the details, let's outline the main questions we'll answer. What are the relationships among angular kinematic variables? How do angular and linear displacement, velocity, and acceleration connect? And importantly, how can we solve quantitative problems involving these angular quantities? By addressing these questions, we'll build a strong foundation for understanding both the theory and practical applications of angular kinematics in human movement. Start with the concept of the instant center of rotation. This is the precisely located center of rotation at a joint at any given instant in time. In human movement, joints don't always rotate around a fixed point. Instead, the center of rotation can shift as the joint moves. For example, during knee extension, the path of the instant center of rotation changes as the knee straightens. Understanding this concept is crucial for analyzing joint mechanics and designing effective rehabilitation or athletic training programs. Better understand the instant center of rotation, let's look at a visual example. During knee extension, the path traced by the instant center is not a simple circle. Instead, it shifts position as the knee moves from a bent to a straight position. This dynamic path is important in biomechanics because it affects how forces are distributed across the joint, influencing both performance and injury risk. By tracking the instant center, researchers and clinicians can gain insights into joint health and function. Now let's define angular displacement. Angular displacement refers to the change in the angular position or orientation of a line segment. It's assessed by measuring the difference between the initial and final angular positions of a moving body. Think of it as the angle swept out by a limb or segment as it moves. This quantity is a vector, meaning it has both magnitude and direction, and it's measured in degrees, radians, or revolution. Understanding angular displacement is key to analyzing rotational movements in sports and daily activities. See angular displacement in a practical context. Imagine performing a bicep curl. When your forearm returns to its original position at the end of the exercise, the angular displacement at the elbow is zero. This is because the initial and final positions are the same, so the net change in angle is zero. However, the total angular distance traveled is not zero since your arm moved up and down. This distinction between angular displacement and angular distance is important for accurately describing movement. It's important to distinguish between angular distance and angular displacement. Angular distance is the sum of all angular changes that occur during movement, regardless of direction. In contrast, angular displacement is the angle between the initial and final positions, taking direction into account. For example, if a pendulum swings back and forth, the angular distance is the total angle covered, while the displacement is just the angle from start to finish. This distinction helps us better describe and analyze complex movements. Angles are commonly measured in degrees, which is a familiar unit for most people. A full circle is 360 degrees, and this unit is often used in everyday descriptions of movement. For example, when you say you rotate your arm 90 degrees, you're using this system. Degrees provide a straightforward way to quantify angular changes, especially in sports and exercise settings where precise measurements are needed for performance analysis. Another important unit for measuring angles is the radian. A radian is defined as the angle subtended at the center of a circle, by an arc equal in length to the radius of the circle. This unit is especially useful in scientific and engineering contexts because it relates directly to the geometry of circles. In biomechanics, radians are often used for calculations involving rotational motion, making them essential for deeper analysis of human movement. Angular kinematics, we use several units to measure angles: degrees, radians, and revolutions. Each unit has its place depending on the context. Degrees are common in daily life, radians are preferred in scientific calculations, and revolutions are useful for describing complete rotations. Understanding how to convert between these units is a valuable skill for anyone studying biomechanics or working with rotational data. Direction of angular motion is another key concept. Rotational motion can be identified as positive or negative depending on its direction. Typically, counterclockwise rotation is considered positive, while clockwise rotation is negative. This convention helps standardize measurements and ensures clear communication when describing movements in biomechanics, sports, and rehabilitation. Angular velocity describes how quickly an object rotates. It's defined as the rate of change in angular position or orientation of a line segment. Mathematically, angular velocity equals angular displacement divided by the change in time. It's measured in degrees per second, radians per second, revolutions per second, or revolutions per minute. This measure is crucial for analyzing the speed of rotational movements in activities like running, throwing, or cycling. Calculate angular velocity. Simply divide the angular displacement by the time taken to complete the movement. For example, if a gymnast completes a 360-degree spin in 2 seconds, their average angular velocity is 180 degrees per second. This calculation helps coaches and athletes monitor performance and make adjustments to improve technique and efficiency. Angular acceleration is the rate at which angular velocity changes over time. It's calculated by dividing the change in angular velocity by the change in time. The units for angular acceleration include degrees per second squared, radians per second squared, and revolutions per second squared. This measure is particularly important for understanding how quickly an athlete or object can speed up or slow down during rotational movement. Find angular acceleration. Take the difference in angular velocity and divide it by the time interval over which the change occurs. For instance, if a figure skater increases their spin from 90 to 180 degrees per second in 1 second, their angular acceleration is 90 degrees per second squared. This calculation is vital for understanding the dynamics of rapid movements and for designing training programs that enhance performance. Kinematics, we use specific units to measure displacement, velocity, and acceleration for both linear and angular motion. Linear displacement is measured in meters, velocity in meters per second, and acceleration in meters per second squared. For angular motion, we use radians for displacement, radians per second for velocity, and radians per second squared for acceleration. Understanding these units is essential for accurate measurement and analysis in biomechanics. Let's compare angular and linear displacement. Linear displacement refers to the straight line distance between 2 points, while angular displacement measures the angle through which an object rotates. In human movement, both types of displacement are important. For example, when you kick a ball, your leg experiences angular displacement at the hip and knee, while the ball travels a linear distance across the field. Angular velocity and linear velocity are closely related. While angular velocity measures how fast something rotates, linear velocity measures how fast it moves along a path. The two are connected by the radius of rotation. Linear velocity equals angular velocity multiplied by the radius. This relationship is fundamental in biomechanics, especially when analyzing limb movements or the motion of objects thrown or struck by the body. Similarly, angular acceleration and linear acceleration are linked. Linear acceleration is the rate of change of linear velocity, while angular acceleration is the rate of change of angular velocity. The linear acceleration of a point on a rotating object depends on both the angular acceleration and the radius from the axis of rotation. This connection helps us understand how forces are transmitted through the body during rapid movement. Now that we've covered the key concepts, let's discuss how to solve quantitative problems involving angular kinematic quantities. The process typically involves identifying the known values, selecting the appropriate formulas, and performing the necessary calculations. Practice with real-world examples, such as analyzing the rotation of a limb or the spin of a ball, will help solidify your understanding and improve your problem-solving skills. Let's work through an example. Suppose a gymnast rotates her arm from an initial position of 30 degrees to a final position of 150 degrees. The angular displacement is the difference between these two angles, which is 120 degrees. This simple calculation illustrates how to determine the net change in angle during a movement, a fundamental step in biomechanical analysis. Now let's calculate angular velocity. If the gymnast in our previous example completes her 120-degree arm movement in 0.5 seconds, her average angular velocity is 240 degrees per second. This value tells us how quickly she rotated her arm, which is useful for evaluating performance and identifying areas for improvement. Angular acceleration. Suppose the gymnast increases her angular velocity from 100 to 240 degrees per second in 0.7 seconds. The angular acceleration is 240/100 divided by 0.7, which equals 200 degrees per second squared. This calculation helps coaches understand how quickly an athlete can accelerate rotational movements, which is important for skills like spinning or flipping. Angular kinematics plays a vital role in sports performance. Coaches and athletes use these concepts to analyze and improve techniques in activities like throwing, jumping, and spinning. By measuring angular displacement, velocity, and acceleration, they can identify strengths and weaknesses, optimize training, and reduce injury risk. Understanding these principles is key to reaching peak performance. Rehabilitation. Angular kinematics helps therapists design effective recovery programs. By tracking joint angles and rotational speeds, therapists can monitor progress and adjust exercises to promote safe, efficient movement. This approach is especially important after injuries or surgeries involving joints, as it ensures that patients regain full range of motion and strength. Angular kinematics isn't just for athletes and patients, it's part of everyday life. Simple actions like turning your head, opening a door, or twisting a jar lid all involve angular displacement and velocity. By understanding the science behind these movements, we can appreciate the complexity and efficiency of the human body in action. Joints are the pivot points for rotational movement in the body. Each joint has a unique structure that determines its range of motion and the path of its instant center of rotation. Understanding joint mechanics is essential for analyzing movement, preventing injuries, and designing supportive equipment like braces or prosthetics. Choosing the right units for measuring angles and motion is crucial in biomechanics. Using degrees, radians, or revolutions appropriately ensures accurate calculations and clear communication. This is especially important when comparing data across studies or working with international teams where unit conventions may differ. Converting between degrees, radians, and revolutions is a common task in angular kinematics. For example, 360 degrees equals 2 pi radians, and 1 revolution is 360 degrees. Mastering these conversions allows you to work seamlessly with different types of data and ensures that your calculations are always accurate. Let's recap the key concepts we've covered. We explored the instant center of rotation, angular displacement, velocity, and acceleration, and the relationship between angular and linear motion. We also discussed practical applications in sports, rehabilitation, and daily life. Understanding these principles provides a solid foundation for further study and application in biomechanics. Angular kinematics is just one part of biomechanics. As you continue your studies, you'll encounter topics like kinetics, dynamics, and the analysis of complex movements. Each area builds on the concepts we've discussed, deepening your understanding of how the body moves and functions. Stay curious and keep exploring the fascinating world of human movement. If you want to learn more about angular kinematics and biomechanics, there are many resources available. Textbooks, online courses, and scientific articles provide in-depth explanations and practical examples. Engaging with these materials will help you build your knowledge and apply it in real-world situations, whether in sports, healthcare, or research. Students often face challenges when learning angular kinematics, such as understanding the difference between displacement and distance or converting between units. Practice and repetition are key to mastering these concepts. Don't hesitate to revisit examples and work through problems until you feel confident in your understanding. To succeed in studying angular kinematics, focus on understanding the core concepts, practice solving problems, and use visual aids like diagrams and animations. Collaborate with classmates or colleagues to discuss challenging topics and share insights. With persistence and curiosity, you'll develop a strong grasp of the material. Biomechanics is a rapidly evolving field, with new technologies and research expanding our understanding of human movement. Advances in motion capture, wearable sensors, and computer modeling are providing deeper insights into angular kinematics and its applications. Staying informed about these developments will keep you at the forefront of the field. Principles of angular kinematics have a real-world impact on health, performance, and quality of life. From improving athletic techniques to designing safer work environments, the knowledge gained from studying angular motion benefits individuals and society as a whole. Embracing this science can lead to innovations that enhance movement and well-being. Here's a quick summary table of the main angular kinematic quantities: displacement radians, velocity radians per second, and acceleration radians per second squared. Keeping these definitions and units in mind will help you approach problems with confidence and clarity. Bridging the gap between theory and practice is essential in biomechanics. By applying the concepts of angular kinematics to real-life situations, you can develop practical solutions for movement challenges. Whether you're analyzing an athlete's performance or designing a rehabilitation protocol, these principles provide the tools you need for success. Let's review the key formulas in angular kinematics. Angular velocity equals angular displacement divided by time, and angular acceleration equals change in angular velocity divided by time. Remembering these formulas and knowing when to use them will make problem-solving much easier. Try this practice problem. If a knee joint rotates from 45 degrees to 135 degrees in 1.2 seconds, what is the angular displacement and average angular velocity? The displacement is 90 degrees and the average angular velocity is 75 degrees per second. Working through problems like this will reinforce your understanding and build your confidence. Here's another practice problem. If a rotating arm increases its angular velocity from 60 to 180 degrees per second in 0.8 seconds, what is the angular acceleration? The answer is 150 degrees per second squared. Practicing these calculations will help you apply the concepts in real-world scenarios. In summary, angular kinematics provides a framework for understanding rotational motion in the human body. By mastering the concepts of displacement, velocity, and acceleration, and knowing how to apply them, you can analyze and improve movement in sports, rehabilitation, and daily life. Keep practicing and exploring to deepen your knowledge. As you continue your study of biomechanics, you'll encounter more advanced topics like three-dimensional motion analysis, inverse dynamics, and muscle modeling. Each builds on the foundation of angular kinematics, expanding your ability to analyze and optimize human movement in greater detail. Thank you for joining this journey through angular kinematics of human movement. By understanding these core concepts, you're well equipped to analyze, improve, and appreciate the complexity of motion in the human body. Continue to explore, ask questions, and apply your knowledge to make a positive impact in your field. This video was based on materials from BME 310, Biomechanics Chapter 11, and incorporates concepts from Dr. Loïc Alzioub and McGraw-Hill Education. For further reading and detailed study, consult your course textbook and recommended resources. Thank you for watching and keep learning.